R is going to be very useful for chapters 10, chapter 13, 14, and 16. R is already pretty useful for chapter 9, but it's going to really shine starting now. So starting in chapter 10. I said this in a previous video. Chapter 12 is a little bit different because we're going to be talking about proportions there, and that's based on the z-test, and R doesn't have a lot of z-test stuff, so that we might need to do by hand. But the rest of it, basically for the rest of the semester, R is going to be super useful. R is your friend. So the quicker you can become friends and become proficient at it, the better. So what I want to do is I want to do this homework question. And again, this is one where they give you the test statistics. They give you the sample mean, the sample standard deviation, and the sample size. And then you're supposed to come up with whether the t-test works or not. And I think the easiest way is to use the t.test function and to actually come up with data sets with these test statistics that you want. So what I want to do is I'm going to use just use x and y as our x1 and x2. You can call it x1 and x2 if you want. I just like single character names. So I'm going to use, let's see, our first sample size is 12. So we're going to have 12 values there. X, I'm going to take and subtract its mean. I'm going to multiply by the standard deviation that we want, which is 2.4, divide by the standard deviation that we have, and add 15. And then we'll do the same for Y. Hopefully this is a really easy thing to do now. We're going to do the same for Y. We also happen to have 12 values. Y is going to be, we're going to subtract the mean from Y. We're going to multiply by 2.3 and divide by the standard deviation that we have, and then we're going to add 16. And now X and Y are our two values that we want. What we need to do here is we need to notice a few things. We're going to notice that, first of all, this is two, we're talking in chapter 10, so we have two populations. So this is a t-test with two populations. This is a pooled t-test. So what that means is that each of the populations, we have two samples, and we're assuming that they're coming from the same underlying population. And then we're trying to determine whether or not they have the same, population mean. And so we're pooled, meaning that we're assuming that they have the same underlying population standard deviation. And so we're assuming that their variances are going to be equal. So whenever you have a pooled test, you put in the var equal equals true, var.equal equals true. And that's how you know it's a pooled test. And let's see, do we need to do anything else here? We're looking for a two-tailed test with alpha equals 0.01 and a 99% confidence interval. So our confidence level is going to be 0.99. And I think that should be it. And so this will just give us all of the values that we want. So we're looking at whether the, let's see, it's a two-tailed test. So that means that we want to know whether the means are equal or not. Okay, and so that's the first part. That's the easy part. Next, we compute the test statistic. Actually, this is also the easy part with R, negative 0.42. Negative 1.042, so just rounded to 3 decimal places. And then if we wanted to find the critical values, we would use the QT function. Our alpha is 0.01, so if I take that and divide by 2, we get 0.05. And so if I want to find this value, let's say I want it rounded to 3 decimal places. And then I'm going to have a negative and a positive value because it's two-tailed. So I want to round, oh, I forgot the degrees of freedom. That's important. So here our degrees of freedom is going to be 22. That's the total number of samples that we have. So 12 plus 12 minus 2. And so our critical values are going to be negative 2.189 and positive 2.189. Okay, so we'll check that. So that looks good. And then you would interpret. Okay, and again, I'll let you interpret how that works, whether the test statistic is in the rejection region or not. I'll leave that part to you. I'm just more interested in talking about R here. So that's how we do this for a pooled test. The only wrinkle that we have, and I should have mentioned this in chapter 9, but I'm going to mention it now, is when we're talking about confidence intervals, R handles one-tailed confidence intervals differently than my MATLAB does. My MATLAB always wants confidence intervals to be two-tailed, regardless of whether the original hypothesis test is one-tailed or not. Confidence intervals are always two-tailed. And so if you want to find the confidence interval, that's part of what you get from this t.test function. Okay, so notice that the confidence interval is there. This works out, this is exactly the confidence interval that my MATLAB would expect because it's two-tailed. You have a two-tailed test. If you have a one-tailed test, now my MATLAB would want a two-tailed confidence interval. So it would be between one number and another. According to R, though, if you have a one-tailed test, it's going to go from negative infinity to some number or some number to infinity, depending on whether it's left or right-tailed, respectively. So if I scroll up to the previous code, so I think this was a chapter 9 thing, here our alternative was less, so that was a left-tailed test. And notice that the 95% confidence interval went from negative infinity to some number. Okay, so R is just going to basically think of one-tailed hypothesis test as infinite intervals, so unbounded intervals, so from negative infinity to some number or some number to infinity. But the book always wants two-tailed confidence intervals. So the moral of the story here is that if you have a one-tailed test for your homework or quiz or exam or whatever, and you have to find a confidence interval, you have to run the t.test function again using a two-tailed test. And then that confidence interval that the test gives you is what my MATLAB is looking for. So you just always want to use a two-tailed test to find confidence intervals from my MATLAB. Okay, so hopefully that's clear enough. Yeah, this one's very similar to the previous one, so I'm not going to worry too much about that. Here, what we want to do is we want to look at, we have a pooled test. And I want to get to where we have a non-pooled test. And so with non-pooled, we're not really going to do anything too differently. It's just that we're going to use, we're not going to put in that var.equal being true code. So let's look here. We have, so two data sets. Again, they both have 15 values in them. So our norm is 15. So this is 15 random numbers from a standard normal distribution. I'm going to take the data set, subtract the mean from everything, multiply by the standard deviation that we want, divide by the standard deviation that we have, add the sample size, and we're done. Y is going to be the same. So also 15 values, subtract the mean, multiply by the standard deviation that we want, divide by the standard deviation that we have, add the sample mean, which is 16. Okay, and then we're going to do a two-tailed test with alpha equals 0.01. So this is going to be t.test. We have x and y. Our confidence is going to be 0.99. And then that's it. We run our test. We get this crazy. So on the handout that we have on the, let's see if I can find it here, on the formula sheet that I have for chapter 10, there's this crazy formula for the degrees of freedom for non-pooled. This delta figure, this triangle is this delta, that's what we get here. That's this 26.713. Now, again, the book likes to round down to the nearest integer. That's the most conservative choice that you can make. So if we were to do anything with this, we would round down to 26 degrees of freedom. So if we're asked to find critical values, we have to remember to round down to 26 degrees of freedom there. So that's that. So let's go ahead and let's do everything with R. Let me get my two windows back that I want here. So we've run our test. We want to find our critical values. So here we have a two-tailed test. So it looks like we're going to do part A. And we want to find the test statistic. That's negative 2.419, so rounded to 3 decimal places. And then we want to find the critical value. So here I'm going to have to go back and find critical values for our alpha is 0.01, so this will be 0.05. we have 26 degrees of freedom, because again, we take this degrees of freedom when we round down. And so since this is two-tailed, we're going to have two of them. We're going to have plus or minus 2.779, because I have to, I don't know why I'm doing fractions here, 0.779, rounded to 3 decimal places. And so those should be our critical values. Notice, by the way, that if I look at the critical values with the actual degrees of freedom that we computed, we'll get something slightly differently. So if I have 26.713 degrees of freedom, I get a slightly different answer. My MATLAB is not going to like that. So you do have to remember to round down to the nearest integer, because that's how my MATLAB wants you to compute the critical values. And then once we have all that, you can interpret. I think question 12 is going to be the same thing with this. It's just going to be right-tailed instead of two-tailed. So really not too much to that. Hopefully that's clear enough. And again, a non-pooled procedure there. The only last thing that I want to look at is I want to look at the difference. Okay, so if I want to look at the difference here. So it looks like question 14 and 15 are about differences. I mean 15 and 16. So here, if these are paired t-tests, then, and I know that because it says use the paired t-test, there's two ways to do these problems. So here the data is actually just nice enough. I can just input the data directly. So we have 20, 19, 4, 21, 6, 17, and 7. And y is going to be the values 18, 18, 1, 15, 2, 18, and 4. And let me just double check that I did this right. So 20, 19, 4, 21, 6, 17, and 7, 18, 18, 1, 15, 2, 18, and 4. Perfect. So those are our data sets. And then we're going to find the test statistic, and we're going to run the t.test, x and y. Our alternative hypothesis is that they're not equal. So it's a two-tailed test. So that's all that. You don't have to do anything there. We're going to put paired equals true. So it's a paired t-test. And then I think that's all we got to do. And then we get our test statistic. The degrees of freedom is going to be the number of pairs minus 1, as we talked about in the video. Our test statistic t is going to be 3.057. And we could find the critical values. We could find QT of, let's see. So we have our alpha is 10%. So I'm looking at 0.05. We have 6 degrees of freedom. And I might as well make do all the work for us. We want to round to 3 decimal places. This is two-tailed, so I'm going to have a negative and a positive value. So it's going to be negative 1.943 and positive 1.943. Those are our critical values. And then you can interpret from there. And then the last thing to do is basically the same thing here. Oh, I'm sorry. There was 2 other ways I wanted to do this question. I wanted to also just mention that when you do the paired t-test, what that really is doing, and the reason why there's 6 degrees of freedom is that you're really just looking at, so you have your data set x and y, you're really just looking at x minus y as your data set. So if you take your values in x and then subtract the values in y, this gives you some data set. You're really just doing a one population t-test there. It's really not too much more to that. So you could do a one population t-test. This will give you some test statistic. Turns out it's 3.057. All of these values are exactly what you had before. And because you're looking at the differences here, because you basically have 7 values in a single population, the number of values minus 1 is your degrees of freedom. So that's why there were 6 degrees of freedom before. So that's why when you go back up here, there's 6 degrees of freedom, because it's a paired t-test. So there's 7 pairs minus 1. So that's another way that you can do these problems. So that's really all that I can think of as far as chapter 10. Okay, so that's chapter 10 in R.